First off, I want to thank Doug Hughes for inviting me to come down. I think this is a wonderful honor. And I want to thank all of you in the audience for staying this long. Oh my God. I know the last slot on a conference is always the worst slot because everybody's half asleep or they're thinking about the airplane they have to catch. So I want to do two things. I want to thank you for being here and apologize because it's not going to be nearly worth all your time. They started off with this video of Weird Al Yankovic, I lost on Jeopardy. You set the bar very high for me. I don't think I can, I don't know, but I'll try. So what am I going to talk about today? I'm going to talk about the system that IBM developed called Watson, which played Jeopardy. And just as a survey, is there anybody, how many people know Jeopardy, have seen Jeopardy? Okay, is there anybody who's never seen it? Okay, there's a couple. Good. Are you being honest or are you just joking? You're living under a rock somewhere. Scotland. Well, you know. Well, okay, so you have good haggis, and I appreciate that. But other than that reference, there'll be no more haggis in this talk. So I will explain a little bit about Jeopardy as we go, but only briefly because Doug told me if I'm not funny, you'll drag me off the stage. Okay, Watson. I'm going to tell you about Watson. And I'm from IBM Research, and I've worked on this project, but I really did not work on a lot of the detailed algorithms. I mean, I understand these algorithms, and I can talk to them, but if you have those kinds of questions, maybe I have to take them offline. But I will say, if you have questions during the presentation, feel free to raise your hand. If I notice you, I'll call on you. If you want to wait for the end, I'm free for the rest of the evening if anybody wants to talk about details. And I want to have a special thanks to the IBM Research Deep Q&A team. They're the ones who made this happen. All right, well, so what are we talking about? We're talking about the difference between search and an expert for question and answering, right? So what do we do in search? We all use Google, right? Years ago, when I was in grad school, what would we do? Someone would say, what's your favorite program? grep, right? Grep was your favorite program. Today, what's your favorite program? It's Google, which is maybe grep on steroids, perhaps. But Google is not Watson. Watson is not Google. And so what are the differences? For something like Google, you as a user have to think about what you're going to do. And we've all made this accommodation, right? Where when we're doing a query, we stop, even for that instant, to think about what it is we need to do to make a question that Google can answer for us. If we phrase it wrong, it's not going to do it, right? And so we adjust. It's a tool. We learn how to use it. And that requires our kind of adjustment. But on the other side, when we get an answer back, we don't get one answer back. We get a series of answers, and we have to drill through it and find the one that we really want. If we go to an expert, we have a natural language query, right? We use English or whatever language we're using. We talk to it, and it has to understand, or the expert has to understand what the question means, right? And they have to produce some useful information that we will then evaluate. Notice that it says understands, right? I'm not going to argue any philosophy, although I would love to argue philosophy. It's one of my favorite things, about whether computers actually understand. And it's irrelevant, actually, for this talk. But what I mean by understand here for the computer is that it's able to parse the sentences and really figure out what we're trying to say, what we're trying to look for. That's what we mean by understanding. And that's what Watson was, in the end, able to do. Okay, so another thing that you probably are aware of is the Deep Blue supercomputer that was able to play chess at human grandmaster play level and beat Garry Kasparov, the current, or at that time, reigning world champion grandmaster. Before that, many people thought that it would never happen, right? Humans would always be better than computers at chess. In retrospect, we can see this problem and say, no, chess is really the computer's domain. Because, why? It is very structured. There's no uncertainty. Positions are positions. Moves are moves. There's no ambiguity in there whatsoever. And so having a computer capable of doing that's not unreasonable. but human language queries, and trying to understand what those mean. That's something that humans do really, really well. And I'm going to show you lots and lots of examples where it's incredibly hard. We don't realize how hard what we do on a daily basis for granted, and we take for granted, really is. But that's the distinction we have to make. Okay, so all right, you guys know this stuff. This question, what's the answer? Come on, come on. Does anyone know if it's greater than 1, less than 1? All right. Obviously, a computer does this very, very fast, very, very easy. Those are easy questions for us. What about a database query, right? You have some database, you want to look up some values. Computers do this really fast, but humans can do that fast too. But what if the database is a terabyte of data? Okay, humans can't do that now, even though it's basically the same problem. How about this? David Jones, right? Computers are really good at matching. But you in the audience were very clever, you clever people. You knew that those two David Jones were the same, right? So did the computer. But what if I give you a terabyte of data? The computer can still do it, but you can't to tell whether it's identical. How about this? Dave Jones, David Jones. The computer said that's different. But you guys, you all know through your years of experience that most people named Dave are really known as David, right? That's their real name. And so maybe not 100% confidence, but you know that it's almost the same person. That's the kind of thing that we do well and computers don't do well, and the kind of thing that we tried to get Watson to do. So another kind of concrete example is Einstein was born in Ulm, Germany, and if you have a database, the computer has no problem at all figuring that out, right? How about this sentence? One day, from among his city views of Ulm, Otto chose a watercolor to send to Albert Einstein as a remembrance of Einstein's birthplace. Now, I think anybody who speaks English knows that this means that Einstein was born in Ulm. But how do you get a computer to figure that out? I mean, what the hell is a remembrance? Well, how does a computer relate the fact that it's a remembrance to the fact that Einstein's birthplace was Ulm? But Watson can from this, and I'm going to show you how. Another example, simple database lookup. Jack Welch was the CEO of GE. So easy. How about this? If leadership is an art, then surely Jack Welch has proved himself a master painter during his tenure at GE. Again, you all know from this sentence, he must have led the company. But having a computer figure that out, how do you do that? This is what I'm going to try and talk about today. And the difference is, the databases that you all know and love, right, are structured. And you have a data field that's, birthplace or whatever, and you just look it up. But when the data is unstructured, you have to have much more complicated querying processes, and we'll talk about these. So now Jeopardy, as a show, is marked by several very important aspects, right? All of the questions that are posed during the show are very broad and from open domains, right? And this is going to be very important for what we do. And the language that's used is often very complex. So giving some examples here, for $200, if you're standing, it's the direction you should look to check out the wainscoting. So first of all, you have to know what wainscoting is. But not only do you have to know what it is, you have to know where it is in a house and around the baseboard, right? So that's where you would look. In cell division, mitosis splits the nucleus, and cytokinesis splits this liquid cushioning the nucleus. Okay, so these are getting hard, right? And, this one for 1,000, the first person mentioned by name in The Man in the Iron Mask is this hero of a previous book by the same author. So now you have to have levels and levels of knowledge here, right? You need to know that that's a book, The Man in the Iron Mask. You have to know who wrote it. I'm not even sure. I think it's Victor Hugo, but I could be wrong. Anyone want to crowdsource this for me? Dumas. Okay, very good. So I failed that one. But you need to know that. And not only do you need to know that, but you have to know who the first person in the book was. I mean, it's not easy. And these are the kinds of things that Watson can do. Now, not only is it difficult, and not only is it broad-ranging, but you have to do it with very, very high precision. Because we're not just talking about giving a list of possible answers. We're talking about giving one answer and saying that that's the right answer. And so you have to be precise. And then you also have to be confident. We found that if you don't have the kind of confidence in your answer, especially in something like Jeopardy, you shouldn't answer because you lose money if you do. Make a wrong guess. So confidence has to be built into the system, as well as high speed, because Jeopardy is a game of speed. Okay, so just for those two guys from Scotland and somewhere else, Jeopardy is like this. You've got this game board, and you've got these questions and categories, and you choose a question. Someone of 3 game players chooses a question, and the question comes up. The MC host speaks that question. When he's done, they beep in with a buzzer, and they say the answer. And if they're wrong, they lose the money according to the board. And if they're right, they win that amount of money. And if you win, you get to choose another. If you don't, the other 2 people can buzz in. And if they buzz in correctly, they get the money. And then there are 2 rounds of this, where the money gets bigger in the second round. And then there's a final round at the very end with a single question, where people can then bet the amount of money that they have. Okay, that's the game. So now, I talked about broad domains. How broad are we talking? Well, you saw there was 15 questions. There are 2 rounds. 30, and then you've got 5 days a week, so we've got 300, and then there's 50 weeks. So what are we talking, 15,000 a year, different questions? Jeopardy's been on for decades, so there are hundreds of thousands of questions out there, and they never repeat. So we can do some statistical analysis on that set, and we did, and we saw that it was very, very long-tailed. If you look at the categories or particular questions, they fall into particular kind of classes, and at the bottom you can see things like group, film, song, But the tail is so long that developing specific algorithms for specific classes is just impractical. And so we didn't do that. We tried to develop generic solutions for these things as the only feasible way to go. All right. So how do we do it? Maybe I should stop. Are there any questions at that point? This is not good. There are no questions. This is maybe you're still. I know it's been a long conference, but I'm going to stop, and I want to have a question next time. So start thinking about questions. All right. This is how it works. We take a large volume of text. In this case, I don't remember if it was 350 or 450 terabytes of textual data from things like encyclopedias, the web, and we parse that with natural language processing to create what we call syntactic frames. The syntactic frames basically identify parts of speech, and those parts of speech create these objects that we can then use to create something called semantic frames, where we develop knowledge about the world. For example, that wainscoting is at the lower half of a wall around a room. So, things like inventors patent inventions, right? Fluid is a liquid. And those numbers suggest that for each kind of statement about the universe, there's some kind of confidence or some probability that that is true. So for example, fluid is a liquid. Why isn't that 100%? And these aren't real numbers, right? I mean, we just put them in there to show you. When I speak, right, I speak very fluid English, right? That is not a liquid, right? But it's how I use the word fluid. So there's so much ambiguity in these kinds of things that we need to have the entire system end-to-end probabilistic and based on probabilities. And then we can also base them on conditional probabilities. So you see at the bottom, people sink 8 balls. But once you add that word in pool, you're playing the game of pool, you sink the 8 balls. So the probability that that's what it means goes up. So let's take an example. We generate multiple candidate answers, right? So I'll show you in more detail how. But we generate lots of candidate answers. Which one is it? Well, we have to use what we call evidence to support various candidate answers on the left-hand side there. But then we look on the right, you see this piece of text may have come from our body, our corpus, 400 terabytes of data. And it says that cytoplasm is a fluid surrounding the nucleus. And that was from some other piece of text somewhere else. So now we can use that to build some kind of model and then to use that to update the probability for a particular truth case. And that's how we do it. So now I'm going to show you examples of why this is really hard and why you have to be very careful. This example is another question from Jeopardy. In May 1898, Portugal celebrated the 400th anniversary of this explorer's arrival in India. Crowdsource? Vasco da Gama, exactly. So we decompose this sentence, and we look at all the various pieces, and then we take another piece of evidence that's in our database because we got some tweet from some twit, perhaps. In May, Gary arrived in India after he celebrated his anniversary in Portugal. So Gary, man, he's a nice guy. We do some keyword matching like someone using Google might do, and says, well, we've got celebrated, we've got anniversary, we've got Portugal, we've got India. It must be Gary. And at some level it was, because if that was his first time, Gary did kind of. But we've got a problem. 400th anniversary, 1898. We don't have any date information. So this is not the correct answer we're looking for. We're looking for Vasco da Gama. So we look at, oops, sorry, that went a little too fast. Yeah, well, I don't know why I did this. Okay, here's another piece of evidence. On the 27th of May, 1498, Vasco da Gama landed in Kappa Beach. Now, there's not as much matching. You can't do keyword matching and use this piece of evidence to support Vasco da Gama. So we have to add more layering. We have to add more inference. And so here are some examples. We added temporal reasoning. So now we know that those dates are correlated. And then we have to add statistical paraphrasing. So landed in and arriving in are conceptually similar. So we can link those even though they're not identical. And then Kappa Beach is in India. So we have to add geospatial reasoning. So once you have those things, you say, hey, this green thing is really supporting Vasco da Gama much better than Gary. And of course, it's still not perfect. So you look for more and more evidence throughout your hundreds of terabytes of data. So let's look at another example. Now, for us, it's not always fun to do these things, but in the game, it's supposed to be funny, and they often include puns in these things. So here's one, a long, tiresome speech delivered by a frothy pie topping. And the clue is edible rhyme time. Any guesses? Meringue harangue, exactly. How do we get there? A long, tiresome speech. That's a diatribe or a harangue, right? A frothy pie topping could be whipped cream or meringue. But then the category down in the lower left, which some of you might not be able to see, says edible rhyme time. We should be keyed on the idea that the solution has to be rhyming. So we take harangue and meringue, but we have to swap them around, right? Because meringue, even though it is a noun, in this context is being used as an adjective. So the system has to actually be able to figure that out. And that's not trivial, even though this is something we do all the time. So it can give the correct answer in this case. Another simple case, this is perhaps the simplest example you're going to see, the divide and conquer that we use here. When 60 Minutes premiered, this man was US president. Now, the only reason I know this is because I've read this before. You take this and you break it down into pieces. When did it premiere? It premiered in 68. Who was president? Lyndon B. Johnson. Done, right? So you have to know those pieces. You have to be able to compose up from the bottom. All right, now here's a good one. Shirts, TV remote controls, and telephones. Any connections there? Buttons, exactly. You have to realize that. You have to be able to make the connections at a high enough level within the semantic net that you've developed to realize that they're all connected by this thing called a button. How about this one? On hearing of the discovery of George Mallory's body, he told reporters he still thinks he was first. And there's some evidence that George Mallory never made it to the top. Of what? Everest, of course. Mallory climbed Everest, and he died up there, and there's some evidence that he never made it up there. But, what do we do? If we look at this piece it has this thing, he was first. So who was first? Hillary was first, so now you know the connection there. Everest, Hillary, and that's the answer, right? Okay. This graph shows a picture of points of real human players of Jeopardy. Okay, on the x-axis, you've got the percent of answers that human attempted, right, in the game, or was successfully able to buzz in for. And the precision is, of those numbers, how many did that person get correct? And the red ones are the world champion, right? The best ever player. The best ever human player. And you can see, if you can see my pointer, which seems to have disappeared. Oh, come on, don't do that to me. Here it is. This one right here. He was perfect. Almost 70% of the time he knew the answer without any errors. That's how good he was. So those red dots are him. The blue dots are other winners. And there were many, many more dots. So this is a subsampling of all the dots. And down at the bottom, sadly, you can see where Watson was in 2007. Barely getting into like the child's level play. I don't even think he was in the child's level play. Okay. So this is where humans are. And how come this is not advancing? Here we go. So how do we do it? This is a very, very high-level view, and I'm sorry that this is about as technical as it gets. We take a question on the left side, and we do this decomposition. We decompose it into a lot of different possible interpretations, right? So again, I told you all this is probabilistic. So you've got a language model. It's probabilistic itself. It's going to talk about all the possible ways to decompose that into viable interpretations of the sentence. Sorry. And then once you have this decomposition, you can do hypotheses, and you can, what's a possible answer? Then you develop evidence scoring for those hypotheses, and then you have to take all of these things and merge them back together. So it looks something like this. You get the multiple interpretations. You get hundreds of sources of potential information, and you take that to develop thousands of evidence processes, and then that broadens out to hundreds of thousands of possible evaluations and scores. So this thing is very, very big. It broadens out, and then it has to get pinched down to a single answer at the end, which is what we do based on the evidence and the confidence scoring. And this is why we did it on a large machine, because we needed to parallelize it. Okay, so now, this is some fun part. But before I jump into the fun part, I want to ask any questions. I know there we have a question. Good.
IBM's expert system, Watson, won Jeopardy after this many years of development?
That's correct. After 4 years.
Please raise your hand.
What is 4 years? Thank you. Yeah. I no one else buzzed in, so. Question. In the graph, the brown line was, let's see, this one. The one at the bottom was what Watson's performance was, and when we first started out. It was very poor compared to the winners. Yes, question. Do I have a graph that shows? Yes. What is yes? Okay. So, any other questions? Yes?
When you're breaking apart the sentences or the syntax, are you ever storing facts that you find out in the sentences? Or later use?
Storing facts? Yeah, during gameplay, you mean?
Yeah.
Yes, we do that. And I have a slide that will address that a little bit. Okay. So, one more question.
Semantic web when you parse your corpus, right?
Correct.
Do you save it for
yes,
use?
it's saved in disk and memory during playtime, right? So you pre-process the big corpus of data, and you create your, for lack of a better word, database of understanding. And then when you do these queries, it's kind of the opposite of a query because it's not a question, it's a statement. When you make these statements, it then goes through that, which is all running on these the Watson machine. And I can talk about that in a little more detail when we get there. Okay, so now I have 2 slides of growing pains, right? When we started out, oh, it wasn't pretty. It wasn't pretty. So these are some examples of what Watson thought about some of these questions. So the category was the American dream, and the statement was, decades before Lincoln, Daniel Webster spoke of government made for, made by, and answerable to them. Crowdsource? Absolutely, absolutely, the people. And Watson? Yeah, so it was very accurate. Yeah, I mean, so this is arguably correct, right? So, New York Times headlines category. An exclamation point was warranted for the end of this in 1918. Which war? Okay, I'll take it. World War I, thank you. Yes. So, Watson? So now, the story here is that the New York Times very, very rarely puts a sentence on the front, an exclamation point in a headline, and certainly not on the front page. I think maybe this was the only time they ever did it. Maybe twice at the end of World War II. I don't know. It's very rare. And clearly that's what he was looking for, but the problem Watson had was the word this. This is the broadest and most difficult category for Watson. This. I mean, that can be anything, right? It's really broad. And the disambiguation becomes very difficult, and very, very early on it had trouble. Category milestones. In 1994, 25 years after this event, one participant said, "For one crowning moment, we were creatures of the cosmic ocean." Moon landing, absolutely. The Big Bang. So now clearly it was looking at creatures of the cosmic ocean, right? So, I mean, there's something going on there. But this was before we had implemented temporal reasoning. So it didn't know that the Big Bang was so much before 1929. So it had problems with this one. Okay, Queen's English is a category. Give a Brit a tinkle when you get into town and you've done this. You ring them. That's right. Now hold on. Anyone who knows English knows that tinkle means something else in English, American English. British English, it does mean to call, right? Urinate. So why did this happen? This happened because we have a slang engine that tries to identify slang, but it was clearly not catching the fact that Queen's English meant British English, right? And so that's why it weighted the American higher and came up with urinate. Okay. Fatherly nicknames. Okay, this Frenchman was the father of bacteriology, Pasteur. Now, can anyone guess what the answer we came up with? No. Now, before you guys start thinking that Watson is a cannibal, I want you to know that How Tasty Was My Little Frenchman was actually a play that was written about 100 years back and was performed. And apparently these Aborigines eat a Frenchman. And so I think Watson was very loosely using Frenchman in this sentence. Okay. World facts. The Denmark Strait separates these two islands by about 200 miles. Any takers? Greenland and Iceland. Watson? Greenland and Taiwan. Now, clearly, it does separate them, and there's some more things in there, too. But we weren't looking for Taiwan, and the reason? This was before we added the geospatial reasoning. So now we get this kind of thing correct. Boxing terms. Rhyming term for hit below the belt. Low blow. Wrong. Well, at least not according to Watson. Right according to what the Jeopardy people thought. Watson? Now, like you say, this is arguably it's correct, right? It is correct, I guess. This is again a slang issue, right? And now this is one of the earliest funny questions that Watson answered. This was before we started using Jeopardy clues. So it doesn't have a category, and it's actually not phrased as a statement. It itself was a question. Watson can handle questions. What do grasshoppers eat? Sorry, typo on my part. Well, I would say leaves. Someone would say grass. Someone would say just about any kind of vegetation. But Watson, no, it's too easy for Watson. Watson would say kosher. Now, I have no idea why Watson came up with kosher, but someone pointed out to me that, under some definitions of kosher, it's arguably correct. Okay, so, so now if you came for the jokes, you can leave now. We're done. Okay, so we're getting back to serious stuff. In order to come up with these answers, however erroneous sometimes, we need to include lots of different types of evidence. And so here I show examples of, on the bottom, different types, like location. This is a geography question. Chile shares its longest land border with this country. So Watson came up with both Argentina and Bolivia. But if you notice, under popularity, Bolivia was much higher, even though it's the wrong answer. Because in the news, there had been lots of articles about Bolivia, and so Watson doesn't know the difference. It just, there are lots of Bolivia things. I'm going to rate it more highly and give the wrong answer. Another example, you'll find Bethel College and a seminary in this holy Minnesota city. Came up with St. Paul and South Bend, and it erroneously chose South Bend. Why? Because it didn't catch the joke, the pun on the word holy, right? So St. Paul, that was the clue. So what we did is we added a new category of evidence for puns. So when we see things in quotes, we think, maybe it's supposed to be a pun, and so then we turn on that pun engine, right? And then we get the right answer. It's a front engine. Yeah, well, okay. In some sense, everything in the system is a front engine because it's, pun engine. Oh. Yeah. So there are lots of different engines in this thing, hundreds of different engines for different cases, but we didn't do it kind of in the way that I said at the very beginning, trying to identify each possible topic, but rather on a much more focused basis like geography, right, and those kinds of things, and puns, much more broad categories than very small. Was there a question out there? Sorry.
It was unable to detect the significance of Minnesota City?
Yeah, well, like I said, we didn't always have geography turned on, so.
Would that have bought it, do you think?
I don't know. It's a good question. But.
And it's rating St. Paul higher depending on location. Before that.
Yes, location, yeah, so. Yeah, it's in these things, there's so much going on under the covers. It's hard to give a definitive answer always. Okay, so now, question over here.
How do you measure reliability of a source?
So, yeah, how do we measure reliability? Honestly, I don't have a good answer for you. I did not work on that. But in some part, it was due to how much evidence was how many cases in our corpus of data, our hundreds of terabytes of data, how many times the evidence appeared in, did it all appear in one document, or were there multiple documents that supported that? And those kinds of things can lead to more confidence.
Was there a concept of the
Yes. That's correct. There was reliability was one of the things. And that's something that has to be added by hand, by human experts. But you could also try to bootstrap that.
How did you monitor and analyze what's going on under the covers in such a complex system?
How did we monitor it? Well, so you're not talking just kind of peak performance flops.
No, if
you're
you get a
talking
weird
about
answer and you want to understand why.
Yeah, well, there was a team of something on the order of 20 people. I don't know if it was less, maybe slightly shy of 20 people, that were working on various aspects of various engines. And so whenever something went wrong, typically, given the answer, you had some insight into, like the case that I showed you over here. Clearly, if Saint was in one of the answers, but Holy was in the clue, and you ignored that, you knew something was wrong with the puns. And so we would direct that to the person that was handling that particular aspect of the engine. So like if you get a rhyming question wrong, you go to the person who's responsible for the rhyming thing. And sometimes you'd have to just discuss these things with people and then come up with hypotheses for what's wrong and then look at it that way. And not asking Watson, unfortunately, but within the team. Was there another question somewhere? Oh, sorry.
On the slide with the Chile, Bolivia, Argentina question, I saw that Bolivia was much more popular, but there was also a bar graph for reliability, as other people were asking about. And the reliability there was a really stark difference between the two. So it seems as though Watson was the answer that was popular rather than the answer that was correct.
This one here. Oh, sorry. Bolivia. Source reliability. Argentina was much higher in reliability. So what you have to realize is that these categories, these different sources of evidence, in and of themselves, they're also weighted. So the weighting that they get depends on many, many factors. So just because the bar may be bigger, that's not indicative of how the system eventually incorporated all the evidence.
So you folks chose to weight popularity more than reliability?
And it certainly seems that way in this case, but I can't say for certain that that's what happened. Sure. Okay. All right. So now, add to all the complexity we've already seen the fact that the various category labels can be very, very deceptive, right? So in the case of U.S. cities, you imagine that the answer should be a U.S. city, right? But you know, in one case it's shuffleboards, the other case it's the Erie Canal. Now, neither one of those is a city, but those were the answers that we were looking for. So just because a category says something doesn't mean that's, you know, you have to, you can't over-restrict yourself, because if you do, you'll prune searches that are actually true and that you'll lower performance. So that that's why we try to broaden out our search space and keep as many of those active as we can before we bring them down using evidence and confidence to a single answer. Question in the back?
I was just noting that country clubs, the topic is being used as a pun compared to the answers in that category.
That's correct.
I think that's fairly common.
Yes, it is. You're right. So categories frequently have puns built into them without quotation marks. And so we know about this and we factor that in. So we'll turn on our pun engine for the categories. So, right. So a mace and a baton they're clubs, but they're not country clubs. And authors. Job wasn't an author, and neither was Romania, as far as I know. Okay. So now this gets back to a question that we had over here on this side. Sometimes, you know, Watson gets it wrong. The category was celebrations of the month, and for some reason, the type that Watson thought this question was day. So it gave a day. Well, it's on a Runnymede. I don't even think that's a day unless they have Runnymede Day somewhere. Scotland, perhaps? No? No, okay. Just checking. But the answer was June. So Watson can use that information and learn from this. So the next time he didn't do much better. But the next time he started thinking that it could be a month, and then finally he starts giving months as an answer. So as humans do this as they play the game. Typically when humans go through, they have a strategy. And they'll start at the $100, go to the $200, go down, down, down. And those easy clues educate the human, right? And so the human will be able to inform themselves. And so we had to build that into Watson so that it could also learn from what the other people were doing.
How much study did you make of the way that human players actually progressed through a game of Jeopardy?
Now, the question is, how much did we study humans? A lot. In fact, some of our strategies were based on human strategies. You might be surprised to find out that 2 books have been written on how to play Jeopardy. You know, you guys think that you're geeks. I mean, come on. They're giving you stiff competition. I think you better work harder. I think that the strategies were a significant factor in our win. And the strategies were driven a lot by what humans did. And we used human play to measure our progress, right? So we compared our progress against real humans. We had 55 games. I was involved with many of them where we actually had 2 humans who had won in the, not just Jeopardy, but in they made it to the Grandmasters. They had won the Grandmaster thing. So they were very good chess players, very good Jeopardy players. And they would play against Watson. And we would record everything, every little detail, and then they would pore over these results and try and figure out how we could improve our bidding schemes and our betting schemes, our choice. And I'll get back to you. So for example, humans frequently start at the top and start walking down so they can learn. Watson doesn't. The categories get harder, but the daily double, which I don't think I mentioned to you before, if you get the daily double, you can bet any amount of money on that daily double. And if you win, you double it or something, right? You double your money. You double your bid. That is typically in the lower rows. So Watson straight away goes to like the 5th or 4th row and starts data mining to find those daily doubles because that's where you're going to get your big payback. And so that's what we would do. And some of the really good players do the exact same thing. So strategy for choice selection and betting were critical, and they were driven a lot by human behavior. I'll get to you. There's a question over here.
During gameplay, did you actually have a way to give Watson the correct answers when it was wrong, so he used that role?
That's a very good question. Did we?
And if so, how did you do it?
So the answer is no. Yeah, regrettably. Let me give a caveat. The question is, did Watson know the other answers from the other players as the game progressed? And the answer is, after each question, when it was over, Watson did learn what the correct answer was, if it was stated, right? But during a particular question, you know how you buzz in, the first person gets to say it. If they're wrong, the second person gets to say it. Watson did not hear. It only saw the text. So it never knew what that person said. It was very frequent that Watson would buzz in and say the exact same wrong answer. It was very painful. Question over here somewhere? In the back.
So, does Watson, in any particular game session, need to ever actually go down the columns to learn?
Sometimes Watson will choose to go down the columns to learn if it has a low confidence in the category. So it looks at the category and says, gee, do I know that? Oh, yeah, I know it's songs or it's politicians. I know that one. But if it's some crazy, punny title, it might start at the top. So there are multiple strategies built in. Yeah.
Why is it that Watson didn't hear?
That we could have done it. We could have made it here. But today, human hearing is still much, much better than translation. I mean, some people might argue with me. In certain cases, we have what we call superhuman translation. That exists. But typically, it's very high noise situations. In low noise, humans are almost always better than computers. And we didn't want to feed incorrect data to Watson. And so we just figured turn it off. And it worked just fine. Oh, way in the back there?
If I remember correctly, because I watched when it was on, when Watson answered, there was something that showed what Watson thought the probability that they would get the question correct. I don't remember what was it? How often was Watson correct when they answered, and how often was Watson correct when it didn't?
Okay, so the question is, what was Watson's performance overall? And I'm sorry, I don't know off the top of my head. I do know that out of the 55 human games we played with Watson, it came in first place 71% of the time, which is pretty good. Was there another question?
So you said that Watson will often go searching for the daily double, but it would seem that strategically you want to build up some cash before you do that. So how do you balance those things?
Well, I don't know the details of the question is, how do you balance finding the daily double when you have no money with finding, you might want to search a little bit, build up some money. Well, you have to take into account the fact that if someone else finds it before you, it's worth 0. So, that's why we go for it.
So you said you studied human behavior in terms of strategy and bidding.
Yes.
Did you follow more rational economic concepts, or did you actually go with like prospect theory and that?
So,
Less rational.
the man who did that work is a good friend of mine, but I don't know the answer to that question. I'm sorry. Okay. So yeah, I promised you this. We're returning back to how the behavior of Watson improved over time. So this is the same graph I showed you before, and where the baseline was at the beginning of 2007, and how it progressed. Yeah, exactly. And that's how, that one graph shows you how we beat the humans in the game. And actually there's an interesting thing. When we were planning this game, planning the match, we were asking, well, what are the likely outcomes? Well, clearly there are 3 outcomes, right? And we said, well, what should we be hoping for? Well, listen, if we lose, the whole thing was a wasted exercise, right? Maybe. I mean, if you did really well but still didn't win, maybe that's good. And if you blew the top off of it, which is what we actually did, it might make people afraid, right? And so I was actually not rooting for that. I was hoping we kind of came in the middle between 2. Then we could say, yeah, we're really good, but maybe you don't have to worry as much. But we did win, and by a large margin. I don't remember the exact numbers. Maybe someone who saw the game did. But it was like 70,000 to 10,000 for the other 2. Question in the back?
When you answer a question, you have to ring in for the question.
Buzz in.
Buzz in. What I noticed when I watched, it seemed like Watson buzzed more quickly than the human competitor.
Yes.
Did you take that into consideration?
Absolutely. There's a slide here that addresses exactly that question. And, okay, I've forgotten it. No. She asked about the buzzing and whether or not the buzzing was fair. And I'm going to address that later, and then you can decide for yourselves whether it was fair. Okay. So I talked a little bit about this already, about the betting and the game strategy. But it's interesting to note the graph in the upper right-hand corner. These are values from real human play. And the bottom axis, which I bet nobody can read, I can't read it either, it's the percentage of the first place, the first place person has a certain amount of money, right? The second place has another amount. So this is the ratio of those 2 things. So if it's 1, the first and second place are in tie. If it's 50%, then the second place person has 50% of the first place person. And then the y-axis is what they actually bet as a percentage of how much money they had. So blue was the, I'm pretty sure blue was the first place and red was the second place. So you can see there's some structure in there, right? The strong diagonal for red is the bet the bank, right? You just bet everything you have hoping that you win. Blue is what the defender does. When he knows he's far enough ahead, he doesn't have to bet everything to win. He's just trying to optimize his winnings so he can kind of be more conservative. And you can see there's some other structure in there. We could talk about that maybe if anyone's interested. So we had dynamic confidences. And yeah, I told you how we learned to adapt to various clue selection strategies. And that was actually a very significant factor in the winning of Jeopardy. So on a single node, a single question would take about 2 hours to run on a 2.6 gigahertz machine. But we parallelized this on about 3,000 cores, and we did it in 2 to 6 seconds, which is what we needed in order to be competitive with humans who answer in that time range as well. I don't know how much performance improvement we could get if we doubled the size of the machine. Could we bring it down to 1 to 3? Probably not. I mean, there are inefficiencies in overhead, but there's definitely an argument to be made that we could have spent more time optimizing. We could have added more hardware, thrown more at this machine, at the problem. But this is where we were. And you'll note that this whole thing is built on top of this thing called UEMA, Unstructured Information Management Architecture, that we developed at IBM. And this gets to one of the questions in the back. You can see this is how Watson renders its analysis, right? It shows its top 3, and if the top 1 is above the threshold, it buzzes in. If it's below the threshold, it won't buzz in. That threshold is adaptive based on things like how confident Watson is in the category, how confident Watson is in the particular question, how confident Watson is based on the relative amount of money it has relative to the next best player. Things like that will adapt its confidence. So sometimes it'll bet really, really small amounts because it doesn't have to. It feels really confident, or maybe it doesn't feel confident. So you see some funny behaviors there. And I mentioned speed already. And I mentioned that first 71% of the time.
What I remember from the show was that the confidence level was pretty fixed each day, but it varied a significant amount from day 1 to day 2. Not very.
Right. The question is that the confidence level seemed to vary from day 1 to day 2. And why? I guess the implicit question is why. Yeah, there is something about the Jeopardy rules that I don't remember that makes the second day of a tournament special. In fact, I guess we're supposed to play 3 games. We only played 2 games, if I remember correctly. That affects the way it bets. It knew that it had already won 1, so it could change its aggressiveness.
The win is based on the earnings of both.
Correct. The win is based on the earnings of both days. So what do we do next? We've done this, right? We've proven that we can beat the best human at this game. What do we try to do now? Well, we try to make this useful to other people. I mean, what was the joke? Someone said that, was it you? That, the Skynet and all this kind of stuff. It's worrisome. It really is something that we would like to make useful for us. And so how do we do that? Here are some potential business applications, right? Healthcare, life sciences, Here are my symptoms, doctor. What do I do? What's wrong with me, right? This is a classic kind of thing that you would like to be able to do. I mean, how many times have you been sick, but you don't want to go to the doctor? It's, I'm not. But, it would be nice to know, right, what it is. Is it Ebola or is it the flu, right? It would be good to know that. And here's something that's near and dear to your hearts, right? Tech support. Right? Every once in a while, you find one tech support person on a telephone call center who really knows their business, and they can answer any. But this is like a small fraction, right? If you could improve tech support with something like this could be valuable for all of us. And then business intelligence, right? Companies today will have large databases. They do these data cubing operations every day to determine, what their sales are in the Eastern Division or something like that, and they want to know how many cars they should be shipping off their assembly lines for this week based on what they sold. They need to have ways of bringing this data together, and they do this today already, this type of analytic thing. But what other kinds of knowledge could they gain if they could query their databases in more natural ways? What other stuff is out there? For example, if you could query the entire internet for various things. Like, we have some examples, and I don't bring them here. And it's not Watson particularly, but there are ways to look at internet statistics about like Coca-Cola and the usage of the word Coca-Cola in tweets. You know, if you could ask something like Watson to tell you what's the significance of this or where, you know, what's going on, this could be very valuable. And of course, government. Who wouldn't love an easy interface to government? So, Skynet, there you go. So here's an example of medical apps. So you have symptoms, but you also have something like family history. You know, do you have high blood pressure in your family? If not, and you have a high blood pressure symptom, that says something different than if you have high blood pressure and your family has a history of it. And then personal history and any medications you're taking. All of these things can be merged together to develop some type of confidence in your assessment of a particular condition. The system that we actually built. Oh, question over here?
Yeah, I mean, if you want to use Watson for something else, like for medicine, I mean, how much tweaking and tuning is actually required?
Okay.
You obviously need to provide a different set of data for it.
Right.
But do you actually need to spend then another year building different engines?
This is a very good question. The question is, how much time to specialize Watson to something else? It's a very good question. I obviously don't know because we are just in the process of doing it now, but consider the tools that we built into the system can be reused. What really would be changing is the data set. So you could take out this corpus of 400 terabytes of data and replace it with the PubMed online or with Gray's Anatomy book, you know, with medical encyclopedias, and run the exact same thing. It may not be perfect, but it would do a decent job. Then,
yeah, but the thing is, you have to actually come up with all these different engines, how you do betting, how you do
okay, so,
very specific for Japan.
yes, right.
Not necessarily applies.
Right. So the question is about adding betting, right? So Jeopardy needed betting, and Jeopardy needed speed. But, you know, for a medical diagnosis, typically a few minutes would be sufficient, right? Typically. Sometimes it's urgent. But we don't need betting, so it actually makes it easier because we wouldn't have to design all that extra stuff. But something like geospatial reasoning would be very relevant if you have symptoms of something like malaria. Well, have you traveled somewhere recently, right? Knowing that malaria is prevalent in northern Africa would be very useful kind of knowledge, and that geospatial reasoning is already there. So a lot of it can be reused. A lot of tweaking would still be required, but the end benefit is definitely worth that kind of thing. Question?
Was the input to Watson always just text? And if so, was there any thought at some point that analysis of the spoken question would have brought additional confidence or additional utility to it?
Yes, okay. So the question is, was it just text that was given to Watson, and what are the other options? Okay, so yes, this was all text, primarily unstructured texts, you know, things from the web. The encyclopedias were put in there, the Bible was put in there, things like that. Jeopardy has lots of Bible questions.
I'm really just thinking of the question during the gameplay, you know, as opposed to just putting in the question textually. If the analysis was done of the speaker of the question during the game, to add additional confidence in terms of nuance or usage. That way.
Yeah, you certainly could do that, and you're doing speech recognition, and you could use prosody recognition. There's this wonderful example of the use of prosody. This guy is pontificating about the language and saying that some languages have double negatives and some languages don't, but sometimes it means positive, sometimes double negative actually means negative depending on the language. But a double positive always means positive. And someone in the audience says, yeah. So that level of analysis, boy, that's tough. Watson cannot do that today, but IBM is working on systems that can analyze prosody in that way. Yeah. So this slide is actually a boring slide. I'm going to skip it. But this is the one you all wanted, so I saved it for the very end. Right? This is the hardware. What did we do it on? What was the platform? It was 90 Power 750 servers, 2880 cores, 3.5 gigahertz. You can read this faster than me, but I'm going to do it anyway. 500 gigabytes per second on-chip bandwidth between the cores on a chip. 10 gigabit Ethernet network to pull all these pieces together. That was a very critical thing because there was a lot of data moving around. Because if you think about this problem, it's not like a physical modeling problem that D.E. Shaw knows and loves, where you have physical locality to some extent, and you're doing a physics calculation. No, you're doing something about information, something very vague. The information that you need at this node could be anywhere. It's like a uniform distribution. And so lots of communication was required. Had 15 terabytes of memory, 20 terabytes of disk. The sustained performance was about 80 teraflops. Blah, blah, blah. That's all. It was 10 racks. So that was the size of this thing. Question?
What does the QA and JIP QA stand for?
A question answer or question and answer.
Thank you.
Was it really only 20 terabytes of disk and not 20 petabytes of disk?
So we could try and do the calculation. There were 9 servers on each rack, and let me do the calculation offline. It could be a typo.
Okay.
Yeah. I don't think petabytes. No. One could hope. I mean, these days you could get a disk, an SSD, with a terabyte, right, from Isilon or something like that, with one. So you just need 20 of them. It seems like you could have a lot more, right? But I don't know the answer, and I'll find out for you. Question?
I have a question, sort of like, in terms of efficiency per dollar spent, does IBM look at how much the human experts have won at Jeopardy? If you could parcel that much money, this much money up, and hire those?
Yeah. The question is, how cost effective was this exercise, I think. And, honestly, I don't know. But in terms of the publicity IBM gets, it's priceless, as the commercial says. In the back?
There have been a number of attempts to try and determine computing capacity in terms of digital equivalents and what's where up here. Do you think that this type of hardware and this type of exercise gets us closer to understanding what the brain is actually capable of?
That's a very interesting question. Does this teach us about human brains? Is that a good summary?
Pretty much. I mean, you've produced a system which has expert level response times and performance. The numbers show that. We're talking nearly 3,000 cores of memory and disk.
Yeah.
Do you think that actually says anything about the brain's actual capacity? I mean, in terms of training tens of years.
So this is your question is very interesting and it's one that I love to think about because I keep thinking about where we are and where we will be in 10 years. And one of my areas of research is exascale computing. And how do we go from petascale to exascale over the next 10 years? And what does it mean for scientific research and for businesses? And I think to do justice to your question, we really should have a beer after this. The algorithms we use are definitely statistically driven, right, and probability based. But I think the insight to do them, a lot of it comes from what we think goes on in the brain. But I wouldn't tie that connection too tightly. At least that's my, in a nutshell, answer. Question back in the back, standing?
Could you talk a bit about the software stack built on top of Hadoop?
Nope. Sorry. It's because I don't know, not because I'm being flippant. Sorry.
You mentioned also that Watson cannot hear. I'm guessing then Watson cannot see. During play, there are music clues and art clues.
Right.
How did Watson do that?
So there are other types of clues, the audio daily double, the video daily double. We made an arrangement with Jeopardy that there would not be any of those videos and audio things in the game. Now, in principle, we could do the exact same thing, and 20 years ago, text indexing was hot research, right? Now, today, video indexing is hot research. It's a little premature to put that into the system, but I fully anticipate it should be possible in the next 10, 20 years to do exactly that. Question?
Yeah, I noticed a couple times during the Daily Double that Watson came up with some pretty amusing numbers that no human would ever come up with, like $28,735.
That's correct.
And this is just purely an algorithmic assessment and optimization of how much it wants to bet.
That's correct.
Yeah.
So the question was, why did Watson make its crazy bids? Some of the humans typically bid in round numbers, 100, 1,000, 500, whatever. Watson gave really crazy. It didn't have decimal places. They didn't allow us to do that. But we would have, or we could have, because it was using probability theory. So it was saying the value, the bid that optimizes your return is this value times this probability plus this value times, and so those probabilities were floating point numbers, and so we got them. So we didn't hide that. We could have rounded them, but we thought it was amusing to leave it there. Yeah, it was. In the back.
Do you have anybody, a team, working on passing the Turing test optimally?
If we do, I'm not aware of it. It would be an interesting thing. There is a contest, right? Sorry?
You would need synthetic skills as well as answering and searching skills.
Presumably. I don't know what would be required to pass a Turing test. Presumably, I would pass. I'm not sure. But I don't want to test. I don't want to do it. I know there's some more questions. Let's just hold them a little bit because I'm almost done. So this is the summary. This is the anti-Skynet slide, okay? So Watson was good. It won. But Watson has 10 compute racks, 80 kilowatts of power, and 20 tons of cooling, right? And the human brain fits in a shoebox. It can run on a tuna fish sandwich, and it can be cooled by a handheld paper fan. So we have a long way to go, I think. A long way to go. And so thank you very much. I'm happy to take more questions.
You said you were going to talk about the buzzer.
Oh, the buzzer, sure. In fact, I'll leave this up later. The buzzer is over here. This is the gameplay, right? Or how it's kind of set up. You've got that clue grid with all the clues. One of those clues shows up. When it shows up, the clue text is sent to Watson. And so Watson starts processing. When Watson is processing, the host, Alex Trebek, starts reading. And Alex, most people don't realize this, has a button, right? And on his podium, when he has finished reading, he presses that button, and that lights a light. When that light comes on, then the buzzers are activated. If you press the buzzer before that, it doesn't do anything. And sometimes if you watch Jeopardy a lot, someone says, gee, I've been pressing it, it's not doing anything. And it's because they tried to do it too soon. So when the thing turns red, they can buzz in. If Watson is ready, if he's finished his calculations, I do this, I say he. It's just because the name is a masculine name. It's an it. When Watson is ready, it will buzz in, but not before. So if the red light hasn't gone on, it will wait, and as soon as it sees the red light, it will buzz in. And it has a mechanical buzzer with a servo motor, so that's how we tried to make it equal, right? But if it's not ready, it won't buzz, and it waits and waits and waits until it has an answer. Now the humans, and one of the biggest advantages of champion-level play in Jeopardy is that humans have the ability to know they know the answer before they know the answer. And so experts, they'll buzz in before they've gotten it in their head. They tell us that this is what they do, and then then they do it. Right? Then they say. And, I mean, that takes some guts, right? And Watson doesn't do that. So Watson has to wait. So is that fair? Sometimes, if the clue is short, then Watson hasn't had time to do enough computation. But if the clue is long, Watson may have done all his computation, be waiting for that red thing. So that's maybe an inequality there. But the fact that the humans can buzz in early is an inequality. So we tried to make it as equal as we could. This is the balance point that we came to. And I already mentioned that Watson can't hear, it can't see, it doesn't do the audio-visual cues, and it doesn't buzz perfectly either. So that, I think, answers your question, right? Okay, question here?
There's two more pieces to that. So it's only because you've chosen not to have Watson buzz in before an answer is complete, right? You could build a probabilistic buzzer that says as soon as the light's on, what's the probability of the possibility? Yeah, you could do that, but you don't get it. That's fine. But on the other side,
That's good. You want a job at IBM? I like that. I like that. I like she's busy.
3 jobs at the moment.
Good.
But the other side of it is that because Watson is not doing visual recognition, and we know that there is a delay in sort of visual processing, it seems that Watson is getting a slight advantage and that it starts actually being able to compute other questions.
Humans can read. Once they read, they don't have to listen to Trebek read the answer. They can.
Right, but still, the visual processing is still slower than the transmission of the bits into Watson.
I don't know. I think I don't know. I imagine that the latency of the cables is probably slower than the light getting into your retina.
Slower than the light, but not slower than reading the data they're collecting.
Yeah, neurons. You've got neurons. Oh, you could have it do OCR, but it's just that's the way humans hardware works, and I don't know. I mean, is it fair? I still don't know the answer whether it's fair, but that's how it was done. Oh, sorry. I thought you were just standing there for fun.
You talked about the potential applications of the technology you've developed. Have you considered the possibility that the lessons you learnt in developing that technology, in particular the tricks you've developed to teach the technology how to understand non-literal statements, could be useful in teaching kids with Asperger's how to better understand natural language as it's used, as opposed to formal, perfectly obvious language?
That's very interesting. I don't think anyone's thought about that.
It's an idea for you.
Yeah, I can certainly send that to the group. The problem is, education just doesn't pay the way banking does.
Yes.
But it is a good idea, and I will talk to the team about that. Thank you. Oh, we have a line over here. I didn't see that line. Please.
So it seems like for a project like this that you must have had, obviously, a well-versed team from all walks of science, the hard sciences, the soft sciences. Was it mostly computer scientists, or did you have linguistics experts?
Oh,
and, what?
Well, there's a very funny story from IBM speech. There was a man, and I can't remember his name. If Watson were here, he could get it for me. But when IBM started doing research on speech recognition in like the 60s, I guess it was sometime maybe early 70s, I don't know. They did it with linguists. They had lots of linguists because they knew language, right? It made sense. But they found out that statistical analysis was much more effective. And that guy who was leading the speech group said, I don't know the exact quote, but it goes something like, our performance goes up 10% for every linguist I fire. And so this is a joke, but it's true, and it's relevant because what we're finding more and more is that it's actually more effective to give the computer data and algorithms that can teach it rather than try and teach it specifically to do things.
So then you had mostly, your most effective parts of the team were your mathematicians, your statisticians, your algorithmic computer scientists.
Right, so computer scientists and people who knew about natural language processing. So those were computer scientists, but they had a very deep basis in probability theory, expectation maximization, maximum likelihood, all these statistical things that allow you to learn from data.
Okay, thank you.
You're welcome. Ping pong, okay.
This might end up with the same answer. You mentioned as you were going through there a number of modules that you wrote for the geographic and the temporal and everything. How much of Watson is those hard-coded sort of things where you realize, oh, we need to model this thing to make him understand something more, versus how much is, as he was getting the text in, he was able to figure out that 1992 comes after 1903 and all of that?
Okay, wait, I think it's not right. Is it 1992, 03? Okay. You threw me off with that one. The answer is I don't know how much. there was a basic foundation for the natural language processing that had been built up over 20 plus years at IBM Research, and that was heavily used. And so, if you count that 20 years, it was a big effort. But if you we took that and that was the basis, then we built on top of that, then most of the effort was in the building on top. And so I guess it's hard for me to say exactly what the ratio is.
Yeah, thank you.
What was the size of the input corpus?
Like I said, I think it's somewhere between 350 and 450 terabytes of text.
The hardware slide said 20 terabytes for disk storage.
Sorry. That was storage during runtime. Yeah, and
tell us more.
To generate the system, it was hundreds of terabytes of data.
Right, and so the semantic web that it built up was then less than 20 terabytes.
Right.
And how much of it was the semantic web, and how much of it was just scratch space for searching?
Don't know.
Okay.
Sorry.
Did you have system administrators on your staff? Did you have system administrators on your staff to help keep the system
Yeah, we had
running?
people. Yeah.
How large was your system administration
staff?
There's
like 1 or 2 people, not a lot.
Okay, got it. Thank you.
I mean, we had more people that were responsible for actually putting the machine together, I think. They were probably the same guys, actually. I'm kind of guessing on the last part, so it wasn't a lot. It wasn't a large staff, small.
Right.
We can't. Everything's done on a shoestring,
Wow.
Yeah.
Did you connect to the Jeopardy game remotely from your usual location?
The game was actually recorded on site at IBM.
Oh, okay. Thank you.
Yeah, we ripped down our whole auditorium and made it look just like the Jeopardy set.
Did you keep the set afterwards?
It's still there. Yeah, we're getting a lot of mileage out of it.
I'm curious, as you obviously spent a lot of time teaching the machine how to work with unstructured text and how to process it. In that, through those experiences, have you considered publishing some of your results, in particular, how we may start to change the way that we produce unstructured text in a way that it might be more easily absorbed by systems like this in the future while remaining unstructured?
So I don't know if you're aware, or probably the audience, you're not aware, NIST, the National Institute for Standards and something, NIST, NIST, has been funding research in this area for a long time, for at least a decade, probably 15 or more years, to do things like question answering, document summarization, entity identification, things like that. And so over that time, certain methods for dealing with unstructured data, text data, have arisen and are being used kind of generically. And UEMA, that Unstructured Information Management Architecture, is an example of one of those that we use as a critical basis for this.
More an observation than a question. But my very first job writing programs was back in 1978. The system had 16 kilobytes of memory, 2 floppy drives, each of which held 400 kilobytes. That was only 33 years ago. So we may not have as long to wait as you think.
Well, well, there's Moore's Law, yeah. Interesting, that's another conversation for a beer, I think.
Is the corpus of data available online for interaction? Can we
Good
query
question.
deep
Is the
QA?
corpus? I don't know. But if you notice on the slides here, there is a URL. If you go to that URL, there's all kinds of information that can help you, and there's probably a link for additional questions there. It's IBM what? Sorry? Oh, come on. Did I put the W3? That's a W3. Try www and see if there's a mirror to that. No? Oh, so this is not good. This is the URL they gave me. Okay. Ignore that page. That page is wrong. Sorry. I'm sorry about that. I really don't know. I'm sorry. I just got the URL. Maybe that isn't internal. Maybe that was supposed to be for me instead of for you. But I apologize if that's the case. Question? I think,
yeah. So a few people have taken you to task already about lack of OCR and lack of speech recognition, which I'm a little amused by because I know IBM makes a pretty good quality speech recognition engine. But is that something you're looking to add to a Watson-like system? So you're talking about healthcare and customer service sort of roles where like medical record OCR might have some value, or if you're accepting phone calls, doing the speech recognition is going to give you all the input you're going to get. You don't get text input.
That's right.
For call centers. Is that something you're looking to add?
Well, like I mentioned earlier, we could easily add that. That technology is already there. But we would only add that if we see a demand for it in a particular application. So call centers is a case where we could do that.
So you're looking for sales opportunities?
Always. And over here?
Might be a silly question. Have you considered actually just connecting Watson to the web and allowing people to actually ask it questions as kind of an ongoing
idea.
demo? I realize you might have to do some rate limiting or some kind of voting or lottery system to give people their chance to ask it the question. But have you considered doing something like that?
That question has arisen before, that idea of allowing that. I don't know if we would ever do that.
Well, I'll take it as a suggestion.
Yeah, it's a good idea, but it's not. It's original to you, I know that, but it's been kicked around before.
It's not original, I don't think. Picking up a lottery system or something to decide how to allocate the slots where people can ask the question might be more interesting.
Yes, I agree. Question?
First, a brief comment to Bill. 16K and 2 floppies, 8K, 4 users, paper tape.
We're going to have a tinkle contest here.
Kids nowadays. But that actually leads into my just a comment, and it occurs to me that what you built as a child, that looks at everything, tries stuff, and figures out what works and keeps doing that.
In a sense, yeah. Over on this side.
So I don't recall this coming up in your presentation. Did you take into account information provenance, where it came from, who wrote it?
Yes, provenance was used to rate confidence. Like Encyclopedia Britannica was rated more highly than Twitter's feeds. I'm not sure if that's correct. But
So ENIAC was 150 kilowatts.
Oh.
But, no, so this corpus of data that Watson munched on, presumably some of the language was a little structured, some was a little bit more structured. So I'm thinking some kinds of the written word are more structured than others, like law. So I'm wondering, could Watson pass the Mass Bar exam?
That's a very interesting question. Wow, we should try that. Definitely try that.
So you mentioned, I think in passing, that Watson has read the Bible, and I won't ask what kind of confidence you gave that particular corpus.
That source. Well, hold on. There are some questions where, like whether or not something is actually textually in the Bible may be a question that comes up. Sorry. Yeah. I know you're joking.
Yeah, I was wondering, I guess I'm joking, but whether Watson has had comparative theology going on, and also whether it's read the laws of robotics.
Oh, the laws of robotics. Probably. I'm almost certain that that's in there somewhere. Yeah. Last question. You get the. But I will be around if anybody wants afterwards.
How did you handle software updates? For example, going from version 0.7 of Watson to 0.8 and so many computers?
Yeah. So I'm very sorry. I don't know the answer.
Is it possible to get an answer to that question somehow?
Sure. Somehow. You'd have to ask the guys who actually did it. They were just using CVS, SVM or something, whatever, and just not SVM, the other one.
Sure.
You know what I mean. And they just were updating it and trying it and testing and slowly doing regression testing and all that. Mm-hmm. Okay, thank you so much, everybody. You're a great audience.